Welcome back to the deep dive. We are tackling something today that feels massive, literally the size of the universe. But we're actually going to start with something incredibly small. A definition. A single word.
It is, yeah. And it's a semantic puzzle, really. But it's the kind of puzzle where once you solve it, you sort of accidentally unlock the architecture of, well, everything.
Right. And I want to start by asking you, our listener, to do something for me. Just, visualize the night sky. You're standing in a field, looking up, you see the moon, maybe Venus shining bright, a whole wash of stars, maybe a streak of a meteor. Now, if I asked you what you were looking at, you'd probably say space objects or maybe celestial bodies. I know I use those terms interchangeably all the time.
Oh, most people do. And why wouldn't you? I mean, to the casual observer, a rock in space is a rock in space. Whether it's a planet, a moon, or a galaxy, it's just a thing up there. But the source material we're covering today, and this spans everything from, IAU technical papers to historical treatises, it makes a hard, distinct line between those two words. A body and an object are not the same thing.
And this isn't just like pedantic grammar policing, right? This distinction actually explains how gravity builds the universe.
Exactly. It all comes down to cohesion. So here's the technical breakdown. An astronomical body is a single, tightly bound, contiguous physical entity. It's one solid or, fluid thing.
Okay, so let's ground this. Earth is a body.
Earth is a body, the moon is a body. A single asteroid just tumbling through the dark is a body. It's held together by gravity or chemical bonds into like a single package. If you kicked it, you'd break your toe on one contiguous surface.
Okay, so contrast that with an astronomical object.
An object it's a structure. It's more complex, it's a system. And it usually contains multiple bodies inside it. So
Yeah.
take the solar system. That is an astronomical object. It contains bodies, the sun, Earth, Mars, all the asteroids. But the system itself, so the collective dance they're all doing, that is an object.
That's a great takeaway right off the bat. A body is a thing. An object is a system of things.
Precisely. A galaxy is an object. A star cluster is an object. But there was one example in the reading that I think really, really nails this distinction. It was the aha moment for me, the comet.
I love this part because the comet feels like it's cheating. It's like a shapeshifter.
It essentially is. I mean,
Okay.
think about a comet when it's way out in the Kuiper Belt. It's deep in the dark, freezing cold. It's just a frozen nucleus, a dirty snowball of ice and rock. At that stage, strictly speaking, it is a body. It's contiguous. It is just a rock.
But then it starts to fall toward the sun.
And it wakes up, it heats up, it starts venting gas. It develops a coma, that fuzzy atmosphere around it, and a tail that can stretch for millions of miles. Once you're describing the nucleus plus the coma plus the tail, you're describing an astronomical object. It has graduated from a simple rock to this dynamic, interacting system of parts.
I love that. It's like the comet graduates from body to object just by having a cup of coffee and waking up. So our mission today is to use this framework. We're going to go from bodies to objects, and in doing so, we're going to map the hierarchy of the entire universe. We'll trace how we went from seeing gods in the sky to seeing data points, and then we are going to take a tour of some of the most terrifying and wonderful exotic objects in the catalog.
From the origins, 13.6 billion years ago to theoretical eyeball planets and synestias?
Yeah.
It's going to be a pretty comprehensive tour.
Let's rewind way, way back. Before we even had these definitions, humans were still looking up. But the relationship was totally different. It wasn't about scientific classification. It was personal.
Oh, it was spiritual, absolutely. But the sources point out something really interesting. It was also surprisingly utilitarian.
Right. The sources really emphasize this dual nature. On one hand, you've got the earliest cultures viewing the planets as deities. Mars wasn't a rock rich in iron oxide. It was the god of war. Venus was a goddess. The movements in the sky were the literal actions of divine beings.
But on the other hand, they were using the sky as a precision tool. We often forget that for most of human history, the sky was the only calendar you had. It was a survival mechanism. The source material notes that agriculture was the primary driver here. If you can't read the stars, you don't know when the frost is coming. If you don't know that, you plant your corn too late, and your entire village starves.
So the sky was a clock long before it was a laboratory.
Exactly. You needed it to separate the seasons. You needed it to navigate across oceans where there were no landmarks. The stars were the original GPS.
I want to jump to the Middle Ages for a second because the text makes a point to highlight this gap in the standard Western education narrative. We usually jump from the Greeks straight to Galileo, but there was this massive era of contribution from the Middle East.
Huge contributions. I mean, while Europe was in a relative scientific stagnation, at least regarding astronomy, scholars in the Middle East were refining the calendar to an incredible precision. They were naming and cataloging stars, and these are names we still use today. Betelgeuse, Rigel, Aldebaran, these are all Arabic names. They were describing nebula long before telescopes even existed. They were keeping the flame of inquiry alive and adding fuel to it.
And meanwhile, in Europe, the focus slowly started shifting toward structure, creating the universities and the textbooks that would eventually facilitate the next big leap.
Which brings us to the scientific revolution. And this is where that definition of body versus object really starts to matter, even if they didn't use those specific words yet. Because suddenly, Earth isn't the floor of the universe anymore. Earth becomes a body.
The who's who of astronomy. We have to start in 1543, Nicholas Copernicus.
The seismic shift. I mean, before Copernicus, Earth is the center. It's the stage. Everything else is just lights on the ceiling. Copernicus flips the script. He publishes the heliocentric model. He says, no, the sun is the center. Earth is just another body moving around it.
And that creates a psychological crisis as much as a scientific one.
It does. It completely demotes us. It takes us from being the protagonists of the universe to just being residents. But then you have Johannes Kepler coming in to provide the math. And Kepler is absolutely vital because he showed that these bodies don't just wander aimlessly. They follow laws, the laws of planetary motion. And that implies a system. It implies a mechanical universe, not a whimsical one ruled by the moods of gods.
And then there's Giordano Bruno, 1584. I always find his story a bit chilling because he was so far ahead of his time that it literally got him killed.
Bruno is a tragic visionary. He looks at the stars and he makes this leap of logic that is just terrifyingly vast. He says, those aren't just lights. Those are other suns. And if they're suns, they must have their own planets. And if they have planets, maybe they have people. He expanded the universe from a closed room to an infinite forest.
A forest he was burned at the stake for proposing.
Unfortunately, yes. Being right too early is a dangerous thing.
Then comes the technology that just changes the entire game. 1610, Galileo and the telescope.
This is the moment of visual confirmation. Galileo looks at Jupiter and he sees 4 little dots dancing around it, the Galilean moons. And this proved, visibly, that not everything orbits the Earth. But I think his observation of our moon is even more important for our body definition.
Why is that?
Because the prevailing dogma at the time was that celestial bodies were made of quintessence, this perfect, smooth, ethereal matter that didn't exist on Earth. Galileo looked at the moon through his glass and saw craters. He saw mountains casting shadows. He saw pits. He realized the moon was a rock. It was imperfect. It was a physical body, scarred and shaped by geology, just like Earth.
It grounded the heavens. It made the sky material.
Right. And once you know it's material, you can study it. Then you have Edmund Halley in 1758 predicting the return of his comet, proving that even those chaotic, scary visitors obey gravity. In 1781, Sir William Herschel discovers Uranus.
Which was the first planet discovered that you couldn't see with the naked eye.
And that is the threshold.
Yeah.
That's when astronomy moved beyond human vision and became dependent on technology.
And that leads us to the modern toolkit. The sources mention this transition from just looking to using photographic plates, and then something called spectroscopy. Can you break that down? The source calls it a fingerprint, but how does that actually work?
Okay, so imagine you're looking at a fire in the distance. You can see that it's bright. But if you have a prism, you can split that light into a rainbow, a spectrum. Now, if you look very closely at that rainbow, you'll see these dark lines gaps where some of the light is missing. Those gaps are caused by chemical elements absorbing very specific wavelengths of light.
So if I see a gap in, say, the red part of the spectrum,
that might tell you there's hydrogen burning or helium. Joseph von Fraunhofer and Angelo Secchi pioneered this. And suddenly, we could look at a star a million light years away and say, that star is made of 70% hydrogen, 28% helium, and a tiny pinch of iron. We went from knowing where a star is to knowing what a star is.
That is just mind-blowing. We basically touch the stars without ever leaving the ground.
And that led to classification. The Hertzsprung-Russell diagram, which I know we'll dive into later, allowed us to sort these bodies into families. And then finally, the great debate over the scale of the universe was settled when Edwin Hubble looked at the Andromeda Nebula and realized it wasn't a gas cloud nearby. It was an island universe, a galaxy.
The universe got a lot bigger that day.
It did. And that brings us perfectly to the structure, the hierarchy.
Right, section 2. We have the parts, we have the history. Now let's look at the assembly. The outline calls this the cosmic hierarchy.
Think of it like a nesting doll, or better yet, a biological structure. It is not random.
The source describes the universe as a web.
It is a web, yeah. If you zoom out to the largest possible scale, the universe looks like a sponge or like a neural network. You have these massive filaments, these great strands made of thousands of galaxies stretching across the dark. And between them, voids, these massive bubbles of almost nothing.
So galaxies aren't just scattered randomly like salt on a table.
Not at all, no. They cling to these filaments. Gravity pulls them together. So you have the web. Inside the filaments, you have superclusters. Inside those, you have clusters and smaller groups. And the fundamental unit of this entire architecture is the galaxy.
Okay, let's drill down on the galaxy unit. The text mentions morphologies, which is just science speak for shapes, right?
Right. And you basically have three main flavors. You have ellipticals, which are these big, fuzzy footballs of old stars. You have irregulars, which are just chaotic blobs, usually caused by a crash between galaxies. And you have disk galaxies, like our Milky Way, these beautiful spirals with arms and a halo.
And lurking in the middle of almost all of them.
The monster.
Yeah.
The supermassive black hole.
The source calls this the active galactic nuclei, or AGN.
That's when it's feeding, yeah. When gas and dust and stars fall into that black hole, it can light up brighter than the rest of the galaxy combined. It's the anchor. It's the gravitational hub that helps hold the whole structure together.
And these galaxies aren't peaceful. I saw the term galactic cannibalism.
It sounds like a great metal band name, but it's real physics. Galaxies collide. Gravity is relentless. If a big galaxy passes too close to a small dwarf galaxy, it'll just rip it apart and consume it. The Milky Way is doing this right now. We are currently in the process of digesting the Sagittarius dwarf galaxy.
We are cannibals.
We are. And eventually, we're going to crash into Andromeda. It's a violent, dynamic ecosystem. And orbiting these big galaxies, you have even smaller subcomponents, dwarf galaxies and these things called globular clusters.
Okay, so we're inside the galaxy now. How does the hierarchy continue downward from there?
Well, the galaxy is made of this gaseous matter that assembles through gravitational self-attraction. That gas condenses to form stars, that's the stellar level. And then around those new stars, you have leftover material, these protoplanetary disks, that accrete to form planets.
So the hierarchy is web to cluster to galaxy to system to body. Debris becomes a body becomes part of a system becomes an object.
That's the chain. That's the architecture.
I want to double click on the stars for a minute because the outline mentions the engine of the universe. We talked about the HR diagram earlier, the Hertzsprung-Russell diagram. Why is this one chart so fundamental that it gets its own section in our deep dive?
Because the HR diagram isn't just a chart, it's a biography. It's the timeline of life and death for the entire cosmos.
Walk us through it.
Okay, so imagine a graph. On the bottom axis, you have temperature, running from hot on the left to cold on the right. On the side axis, you have luminosity, how bright it is, running from dim at the bottom to bright at the top. Now, if stars were just random, they'd be scattered all over this graph. But when Hertzsprung and Russell plotted them, they realized they weren't random at all. They clump.
They clump into a line.
Exactly. There's this distinct diagonal band that runs across the graph called the main sequence. This is where stars spend about 90% of their lives. Our sun is parked right there, smack in the middle. It's stable, it's happy, it's just burning hydrogen into helium.
But they don't stay there forever.
No. Stars evolve. And this is the key insight. A star's position on this graph tells you its future. As our sun starts to run out of hydrogen, it's going to peel off the main sequence. It'll move up and to the right on the diagram, becoming a red giant. It gets cooler, so it gets redder, but it gets much, much bigger and therefore brighter.
And what about the instability strip? That sounds ominous.
It's a turbulent neighborhood on the graph. Stars that are passing through this region on their evolutionary journey can't find their balance. They physically pulsate, they grow and shrink. And we can use these stars, like the famous AFI variables, as cosmic yardsticks because their pulsing creates this very distinct pattern we can use to measure vast distances.
So the star is born, it joins the main sequence, it ages into a giant. How does it die? The source outlines the end games.
This is entirely determined by one thing: mass. Mass is destiny for a star.
Okay, so let's take a medium star, like our sun.
It's a relatively gentle death. It puffs off its outer layers into space, creating this beautiful glowing shell called a planetary nebula.
Which we should probably clarify has absolutely nothing to do with planet.
Nothing at all. Early astronomers just thought they looked around like planets in their blurry little telescopes. The name stuck. But inside that colorful shell, the core of the star remains. It becomes a white dwarf, a hot, incredibly dense ember that just slowly fades away over billions of years.
And for the massive stars, the real rock stars of the universe.
They live fast and die violently. They burn through their fuel, they fuse heavier and heavier elements, and then boom, a supernova. The explosion outshines its entire galaxy for a few weeks.
And what's left behind after that?
The most extreme bodies in the universe.
Yeah.
If the star was heavy, you get a neutron star. A city-sized ball of neutrons so dense that a single teaspoon of it would weigh 1 billion tons. And if it was very heavy, you get a black hole, a puncture in space-time itself.
It's humbling to realize that the iron in our blood, the calcium in our bones, all of it was cooked inside those massive stars and then blasted out in those explosions. We're literally nuclear waste.
Or, stardust, recycled.
Okay, I want to shift gears to something that seems really simple on the surface but is actually super technical. Shape. Why are planets round?
This brings us right back to that fundamental definition of an astronomical body. The International Astronomical Union, the IAU, actually uses shape as a core requirement for being a planet. The term they use is hydrostatic equilibrium.
Hydrostatic equilibrium. That is a mouthful. What does that mean in plain English?
It means the battle of the bulge. It's basically a fight between two forces. On one side, you have the rigidity of the rock or the ice. The material itself wants to hold its random, lumpy shape. On the other side, you have gravity, and gravity wants to pull everything toward the center equally.
So if you have enough mass,
Gravity wins. It crushes the high points, it fills in the low points, and it forces the material to basically flow over geological time until it settles into the most efficient shape possible, a sphere.
so roundness is kind of like a badge of honor. It means I have enough gravity to conquer my own rockiness.
That's a great way to put it, yeah. It means you've achieved equilibrium.
The source gives a great comparison here. Ceres versus Eros.
Right, so Ceres is a dwarf planet in the asteroid belt. It's large enough that its own gravity has pulled it into a sphere. It has reached hydrostatic equilibrium. Eros, on the other hand, is just an asteroid. It's much smaller. It looks like a lumpy potato or a peanut. It hasn't reached that equilibrium. It's just a shard.
The source also mentions an interesting in-between case for Vesta.
Ah, Vesta. The tragic middle child of the solar system. It's a massive asteroid, or a minor planet, out in the asteroid belt. It is almost round. It's large enough that it actually underwent planetary differentiation, which means the rock melted and the heavy stuff sank to the middle to form a core, just like Earth. But it's not quite in perfect equilibrium. It's sort of stuck in the middle class of the solar system.
And what about SSSBs, small solar system bodies? The text calls them rubble piles, which does not sound very sturdy.
And it's not. Many asteroids, they aren't solid rocks. They're collections of smaller rocks and dust that are just loosely held together by their very weak gravity. If you spun one too fast, it would just fly apart. They aren't fused bedrock.
And stars, they're around too, obviously.
Yes, but for a slightly different reason. Stars are made of plasma, which is a free-flowing fluid. So gravity has a really easy time pulling them into a sphere. However, because they spin, they often bulge at the equator. Even Earth does this a tiny bit, but some stars that spin really fast can be quite distorted, almost like a pumpkin.
Okay, now we get to the fun part, the lists. The source material has these massive lists of categories. Locations, types, theoretical objects. I want to take a tour of the exotic. This is where the universe gets weird. Let's start with planetary oddities.
The extrasolar planets, this field is just booming right now.
One term that jumped out at me immediately was hot Jupiter.
This was one of the first types of exoplanets we ever discovered, and it was a complete shock to the system. We have Jupiter, which is cold and very far from our sun. But a hot Jupiter is a gas giant that orbits incredibly close to its star. I mean, closer than Mercury orbits our sun.
So it's just cooking.
It is roasting. The temperatures are immense. It completely challenged our models of how planetary systems form because we didn't think gas giants could even exist that close. The theory now is that they likely formed further out and then migrated inward, just bulldozing everything in their path.
Then there's the rogue planet.
A very lonely concept. These are planets that have been ejected from their star systems. Maybe two planets got a little too close, and gravity slingshotted one of them out into interstellar space. Now it just floats freely through the galaxy, untethered to any sun, drifting in eternal darkness.
That is both terrifying and beautiful. But the outline also mentions some theoretical planets. Things we haven't seen yet, but the math says could exist. Eyeball planets. Please explain.
Okay, so this can happen when a planet is tidally locked to its star. That means one side always faces the star eternal day, and the other side always faces away eternal night.
Like our moon is to Earth.
Exactly like the moon. So you have a day side that is scorching hot, maybe it's a magma ocean. You have a night side that's frozen completely solid. But in the transition zone, the terminator line between them, you might have this temperate strip where liquid water could exist. If you look at it from space, especially if there's water, it would look like a giant eyeball, a pupil of open ocean or scorched rock surrounded by an iris of ice or clouds.
Wow, and the Chthonian planet. That sounds Lovecraftian.
It refers to the Greek underworld. A Chthonian planet is what's left over after a gas giant orbited so close to his star that his atmosphere got completely stripped away. The star's radiation literally blasts away the gas, leaving only the dense, rocky, metallic core. It's the skeletal remains of a giant.
And ocean planets are just what they sound like.
Yep. Planets completely covered in water, no continents, just a global sea, potentially hundreds of miles deep. The pressure at the bottom would be unimaginable. It might not even be liquid water down there, but strange forms of high-pressure ice.
Let's move to stellar curiosities. We talked about normal stars, but what about the weird ones? The source lists brown dwarfs.
Brown dwarfs are the failed stars. They're the bridge between giant planets like Jupiter and actual stars. They form like stars, collapsing from gas clouds, but they just don't have enough mass to ignite stable hydrogen fusion in their cores. They just glow dimly from the heat of their formation and slowly cool down forever. They come in spectral types, M, L, T, and Y.
And Wolf-Rayet stars.
These are the rock stars I mentioned. Living fast and dying young. They're massive, incredibly hot stars that are blowing their outer layers into space at terrific speeds. They're rapidly losing mass. They're on the absolute brink of exploding as supernovae.
The outline lists some hypothetical stars, too. The quasi-star.
This is a wild concept from the very early universe. A quasi-star would be an extremely massive star, larger than anything that exists today, that has a black hole forming inside its core. The energy from the material falling into the black hole is what keeps the star from collapsing. It's a star powered by a black hole.
And the Thorn-Utko object.
A similar kind of vibe. It's a theoretical object where a neutron star has been swallowed by a red giant. So you literally have a star inside another star.
It sounds like science fiction, but this is all based on the physics we know. Let's talk about galactic powerhouses, blazars and quasars.
These are both types of active galactic nuclei. So remember that supermassive black hole at the center of a galaxy. When it's actively feeding, it can emit these massive jets of energy. A quasar is one of these, shining brighter than thousands of galaxies combined. A blazar is a specific type of quasar where that jet of energy happens to be pointed directly at Earth.
So we are looking right down the barrel of the gun.
Exactly.
And voids. We mentioned the cosmic web, but the empty spaces themselves have names too.
The supervoids. These are vast regions of space with very, very few galaxies. But the source does mention void galaxies. These are lonely galaxies that exist out inside these empty spaces, totally isolated from the rest of the cosmic web. They evolve in complete solitude.
I feel like we've covered the solid, the liquid, the plasma, and the void, but Section 6 takes us into the unknown, the hypothetical, and the future. What are we still looking for?
Well, the biggest elephant in the room is, of course, dark matter.
And the source mentions machos and WIMPs.
Astronomers love their acronyms. We know there is more gravity in the universe than there is visible matter. Something is holding galaxies together so they don't fly apart. One idea is that it could be machos, massive compact halo objects, things like black holes or brown dwarfs that are just very hard to see. The other leading idea is WIMPs weakly interacting massive particles, some kind of exotic subatomic particle that just passes right through us without a trace.
And cosmic strings. That sounds biblical.
They're hypothetical, one-dimensional topological defects. Think of them as cracks in the very fabric of space-time left over from the chaos of the early universe. They would be extremely thin, but incredibly dense. If one passed through Earth, it would be bad.
Finally, there's one term in the minor planets category list that I saved for last because I had to look it up and it blew my mind. Synestia.
A synestia, yes. This is a relatively new theoretical concept. Imagine a giant impact between two planet-sized bodies, a really high-energy, high-spin collision. The rock doesn't just melt, it vaporizes.
Vaporized rock.
Yes. And the whole thing spins so fast that it flattens out into this donut shape. A torus of vaporized rock and gas. It's not a sphere anymore. It's this continuous puffy donut. That's a synestia. Eventually, it would cool down, droplets of magma would rain down inside it, and it would condense back into a planet, maybe a moon. In fact, some of the newest theories suggest the Earth and Moon actually formed from a synestia.
A donut of vaporized Earth. That is a heck of an image to end on.
It completely redefines what an object can even be. It shows that our neat little categories of planet and star were just snapshots in time.
So to bring this all home, we've gone from the very definition of a body versus an object, through the history of how we figured all this out, down the hierarchy of the cosmic web, through the life cycle of stars, and into this catalog of the weird and wonderful.
It's a journey of scale, from the smallest rock to the largest structures imaginable.
So to wrap this up, what's the main takeaway here?
The takeaway is structure. The universe isn't just a container for stuff, it's a hierarchy. You start with debris. Gravity pulls that debris into a body. Bodies interact gravitationally to form a system. Systems gather into a galaxy. Galaxies cluster into groups, and those groups form the web.
And everything we've talked about fits into that architecture somewhere.
Everything, from the frozen nucleus of that little comet to the largest filament of the cosmic web.
I want to leave our listener with a final thought. We started by looking up at the night sky. The source tells us the earliest objects in the universe began forming 13.6 billion years ago. We used to look up and see gods, then we saw calendars. Now, thanks to things like the HR diagram and spectroscopy, we see data points.
We see the physics playing out.
But here's the question for you to mull over tonight. When you look at that static canopy of stars, those little pinpricks of light, try to see them not as fixed points, but as snapshots. You are looking at a frozen moment in an incredibly chaotic movie. You're seeing stars moving along their evolutionary tracks. You're seeing gas clouds collapsing. You're seeing rubble piles just tumbling through the dark.
And if you could just speed up time, you'd see the whole thing breathing, merging, exploding, collapsing.
Exactly. And think about those SSSBs, the small solar system bodies, the lumpy leftovers. We live on a round, beautiful, hydrostatically equilibrated world. But out there are the building blocks that didn't make the cut. The lumpy, chaotic leftovers that tell us just how messy the birth of our orderly home really was.
We're the lucky ones that got rounded out.
We sure are. Thanks for taking this deep dive into astronomical objects with us. Keep looking up.
And keep wondering.